My name is Quan Yu Liu, a staff scientist here at Q-Chem Pleasanton. It's my pleasure today to introduce Professor Tim Neudecker. He'll be talking to us about geometry optimizations and AIMD simulations of molecules under pressure. Tim is assistant professor of theoretical chemistry at University of Bremen. Tim got his PhD in Andreas Dreuw's group at Ruprecht-Karls University Heidelberg, and then joined Martin Hagorn's group at UC Berkeley as a postdoc. His research focused on the development of quantum chemical method under various external influence like pressure and mechanical forces. Without further ado, I'm going to turn this over to Tim.
Yeah, thanks a lot for the nice introduction. Yeah, I hope everyone can see my screen and the pointer. As you mentioned, today it will be all about molecules under pressure. Not completely about molecules under pressure. We're also going to have a very short block at the end of my talk devoted to molecules under external stretching forces, but the focus will be on molecules under pressure. Yeah, it basically all started back in, say, 2018 when I did my postdoc in the group of Martin Hagorn at UC Berkeley. And a co-worker of mine, Ruprecht-Karls and I, we were thinking about an interesting effect in chemistry. We looked at metal ions in octahedral ligand fields, and undergraduate chemistry tells you that yeah, basically you get a splitting of the d orbital energy levels, and depending on the electronic how many electrons the ion has, you can get for example a high spin configuration, and you get this when the energy splitting between the T2G and the EG orbitals is pretty low. Then for the molecule, for this complex, it's more efficient to not pair the spins because you get the favorable exchange interaction. Now, we were realizing something that has been known in literature for quite a long time. If you push the ligands towards the metal, you increase the influence, the electronic influence that the ligands have on the metal. And if you do that, the average metal ligand distance decreases, which leads to an increase in the d orbital splitting energy. And at some point, if your ligands are close enough to the metal, you get spin pairing and you transition from a high spin configuration to a low spin configuration. And what has been known in literature is you can induce this by applying pressure, right? You compress the molecule, this complex, and you get this splitting. Yeah, this makes sense, and we just wanted to model this computationally, and we thought about how to do that. We looked into the literature, and we were looking for methods, for quantum chemical methods to apply pressure to molecules. And we stumbled upon a nice idea that was developed at the University of Southern Mississippi, and this is called the GFMPES, the Generalized Force Modified Potential Energy Surface. And the basic idea is the following. Say you have a triatomic molecule with atoms 1, 2, and 3. You simply calculate the molecular centroid or the geometric centroid in a non-mass weighted fashion, and you add certain forces or you add certain gradient contributions for each atom that point towards the molecular centroid. There are a couple of intricacies. You need to ensure that the forces acting on the outermost atoms are larger than the forces acting on the inner atoms. Only in this way you can avoid any translations and rotations. We thought a little bit about this theory. We did a couple of modifications, and we gave it. We implemented this in Q-Chem, and due to the modifications, we felt that we would like to give the method a new name. So Romit and I, and so this basically was my previous name. Romit and I implemented this in Q-Chem, and we call it HCFF, hydrostatic compression force field. And the main difference between our method and the GFMPES is that we're using the molecular van der Waals surface as the point where the molecule interacts with its surrounding. We would like to model experiments in, for example, a diamond anvil cell more closely. That was the picture you saw in the very beginning. And this was quite easy to implement. It's just a modification of the nuclear gradient. And we just gave it a go. We tried a couple of metals and octahedral ligand fields. And just to give you an example, we looked at iron 2 and an octahedral ligand field of 6 hydrogen molecules. And let us first look at the right y-axis and the average metal ligand distances. You see that with increasing pressure, no matter if you look at the high spin or the low spin configuration, the average metal ligand distance decreases. That's what you would expect chemically and physically if you apply pressure. And then we calculated the energy difference between the high spin and the low spin configuration. And we see this also decreases smoothly, and at some point it passes through 0. And if this passes through 0, it becomes more favorable to generate or to have the low spin state. And this is our crude guess for the spin transition or the spin crossover pressure. In this case, it's around 1.2 gigapascal. Of course, in experiments, you always have a very tremendous contribution by temperature. Pressure-induced spin crossover almost never occurs alone. You always need to, so this temperature where you have half high spin and half low spin is very important. That's something that we're neglecting here because we're doing static geometry optimizations. Yeah, and also we're doing just plain DFT, no active spaces or something like that. So we expect qualitative results at this point. But we are kind of encouraged by the results that we got. For example, we looked at 5 different metal ions in total and 3 different ligands. Let us start with carbon monoxide, for example. There are some entries missing here. And the reason is that low spin is already more favorable at 0 pressure. Again, if we think back to undergraduate inorganic chemistry, we learned that carbon monoxide is a strong field ligand. It has a very tremendous influence, electronic influence on the metal, and in many cases it already leads to low spin configuration. An exception is manganese 2+, but we only need rather low pressure here. And then if you move to the right, you move along this so-called spectrochemical series. H2 is a weak field ligand. It doesn't have a lot of electronic influence on the central ion. So if you move from the left to the right, you see an increase in pressure. That's chemically intuitive and was kind of encouraging to see that this very simple method gives us intuitive results for spin crossover. Now, if you want to try this, if you just want to try this yourself, this is what you would need to do in order to invoke this in Q-Chem. Your $RAM section is quite similar to a regular geometry optimization. Job type opt, you also include a method and a basis. And now what you need to do additionally, in addition to your other keywords, you would need to specify distort true. And this distort true necessitates another section, this $distort section. And this is where all the fun begins. For model, you put HCFF. That's what you want to use for applying pressure. Here, pressure, you put in the pressure in megapascal. So this would be 5 gigapascal. And then there are 3 additional keywords. For these, there are also defaults. You don't need to specify them, but just to give you an idea what they do. Scaling 1.0. Scaling means this is the scaling factor of the van der Waals radii of the atoms. Here we use 1.0, that is just the unscaled van der Waals radii. If you know a lot about PCM, in PCM they use 1.2 in order to account for the remaining distance between the solvent molecules that are simulated and the solute. Here we use 1.0. There's also a paper that finds out that depending on the pressure, you have different van der Waals radii. And here we use as a compromise a smaller scaling factor compared to PCM. And then you also have these two endpoints here. What you're doing in order to generate this van der Waals surface that is used in HCFF, you need to discretize the surface. And you're doing that by applying or by specifying a certain number of tessellation points per atom. And you can do that for the non-hydrogen atoms and for the hydrogen atoms. In basically all cases, we found that 110 is quite enough. And for HCFF, it basically doesn't matter how many you take. There's no additional overhead in the cost. So this is not really important for us right now. Yeah, so we looked at the spectrochemical series and some spin crossover, and we thought, great, let us try some other molecules. For example, some simple alkane. Here you have butane at 0 gigapascal, and we applied a high pressure with HCFF. And we are kind of surprised to find that we get this. This is horrible, right? This is not what you would expect chemically or physically from butane at high pressure. And we scratched our head a little bit. Why is this the case? Is this a bug or a feature? And we quickly realized that this is a feature. And HCFF is actually quite similar to the situation in stars or planets, where you have strong forces pulling every particle towards the centroid. And planets and stars are spheres. And HCFF tries to generate spheres out of every molecule you feed it. And yeah, this gives you these unphysical geometries of extended molecules. We were kind of lucky with our octahedral ligand fields because they, octahedra are mostly centrosymmetric. So this was never a real problem in this study. But with these alkanes or quite a lot of other molecules, this actually is a problem. What we instead want is something like, is really truly hydrostatic pressure. So this scuba diver, for example, if they're underwater, they feel pressure, but they feel hydrostatic pressure. So this person's arms and legs are extended. They're not folded into a sphere, luckily. And instead, at each surface point of this person, you feel they feel a force or a pressure perpendicular to their surface. And this is what we want to have. And before specifying how we did that, let me give you an intermediate summary of HCFF. We could model spin crossover qualitatively, but it gave us completely intuitive results. Geometries, I put a little question mark next to that because for these octahedral metal ligand complexes, it worked fine. But for many other molecules, it doesn't work that well, at least at high pressures. Also, something I did not mention is you cannot specify the pressure a priori in HCFF. It's just the way how the pressure is applied to the molecule basically leads to this. Yeah, you can input a gas for the pressure, but the pressure that you apply is calculated afterwards. And usually the pressure that is applied is like, say, 70 or 80% of the pressure gas that you put in. That is also another disadvantage. So we came up with another model. It's an extension of HCFF, so we call it X-HCFF for extended hydrostatic compression force field. And we look in more detail and at this surface tessellation. For example, this is the water molecule with a discretized surface. And then we focused, for each atom, we focused on those tessellation points that were generated by this atom or that belong to this atom. If you look at this more closely, let us focus on this one hydrogen atom here. The blue spheres here are the tessellation points that belong to this hydrogen atom. Now we draw lines between each tessellation point and this atom. And yeah, basically the elongation of these lines is a gradient contribution that you add. And this gradient contribution can be calculated quite simply by this basic equation of pressure. Pressure is just the normal component of the force divided by the surface area. And for each surface tessera, you know the area. It just pops out of your routine. You know the pressure that you want to input, and it's just a matter of then calculating the normal component of this force. Then there are a couple of intricacies, or not intricacies, but a couple of features. Opposing tessellation points basically cancel each other, and the net force, you basically just add up all the vectors, and the net force is this thick black arrow, or this gradient contribution here. And it turns out that this is really modeling hydrostatic compression very well. You always get gradient contributions perpendicular to the surface. Now let us have a look at what happens with our extended molecule. It turns out with X-HCFF we don't have this problem that everything is folded into a sphere. We get this chemically intuitive extended structure of butane. And of course some bond length change, bond angles change, but that's just what we would expect under pressure. So the geometries seem to work. What else can we do? One example is spectroscopy. Quite surprisingly, there's a molecular crystal called ATD, and here we looked at the CH stretching vibration. It's Raman active, and experimentally it was found that when you apply pressure to the molecular crystal, that the wave number of this CH stretching vibration increases. And what we did is simply doing geometry optimizations of this isolated molecule under pressure, and we almost got the exact behavior, right? So we just put in this distorted geometry into a frequency calculation, and without changing the frequency code or adding any contributions to the Hessian, we're kind of surprised to find that we get almost the exact behavior of this stretching vibration. The only thing we needed to do is to align the zero pressure peaks and scale the spectrum accordingly, but everything else worked. Yeah, we also tried some calculations, for example, or some chemical reactions. For example, the CO2 dimer. You put it just in a van der Waals complex and you measure the distance between this C atom and a neighboring O atom. And if you increase the pressure, we get a decrease in this distance. The van der Waals complex gets pushed together. And then between 90 and 100 gigapascal, we get a formation of a dimer. And these dimers or even polymers have been described in the literature, also computationally. And it was good to see that we get these features as well. Yeah, what do you need to do to try out X-HCFF calculations yourself? It's pretty simple. It looks almost the same as in the HCFF case. You just need to put in X-HCFF as your model in the $distort section. But it turns out that X-HCFF is also not the perfect method. For example, let us look at the energetics of hydrogen, the hydrogen plus ion. Or H2 plus hydrogen molecular ion. There has been a paper from the late 80s where they applied pressure by a rather sophisticated model. They put H2 plus inside a spheroidal box with different wall potentials, and they calculated the pressure that they can apply. And they saw that the energy increases with increasing pressure. That's also intuitive. So how we tried that with X-HCFF, and what we get simply looks horrible, right? So the energy does not increase at all until this pressure here. Then in the end, you see a tiny little bit of increase, but it's just qualitatively a different curve. Again, we scratched our heads. Why is this the case? And again, we quickly realized we have a problem in X-HCFF because what we are doing is we're applying forces to nuclei. And you push the nuclei together and the electrons adjust to this new nuclear configuration. They are more confined, but they are not as confined as they should be. Because in the experiment, or in this wall potential case here, what you're doing is you're confining the electrons. If you, for example, have a diamond anvil cell, you have a solvent that is used to transmit the externally applied pressure to your solute. The electron clouds of the solvent they also interact with the electron clouds of the solute. And what happens physically is that you first compress the electron cloud and the nuclei follow. but we're doing the other way around in X-HCFF, and this is not correct electronically, and this leads to some problems as we see here with energetics. And before I'm going to introduce another method that tries to address these problems, let us amend our intermediate summary. We were quite surprised that with X-HCFF we get Raman spectra quite right. We get physically correct geometries in all cases, basically, in contrast to HCFF. We could model chemical reactions. We can indeed also apply the pressure a priori. So what the user inputs, for example, 10 gigapascal, this is what is applied physically in X-HCFF to the nuclei at least. But here, the electron density, yeah, it's not compressed as much, and there's no direct influence from the pressure on the electron density. And we wanted to solve that, and we were again inspired by a very nice method that was reported in literature. This method is called XP-PCM. It was developed in the CAMI group, and XP-PCM stands for Extreme Pressure Polarizable Continuum Model. I'm not going to go into much detail how this is done, but in comparison to regular PCM for your implicit solvation, you're doing a couple of changes. The first change is that you're shrinking the cavity that basically houses the molecule, and you're also increasing the interaction terms between the solute and the surrounding implicit solvent. And both of these effects are found in diamond anvil cells. You're pushing all the solvent molecules closer to each other, and you're also increasing the electronic interaction between a solute and a solvent. Yeah, and we were, like I said, we would like to model the electronic interaction of the environment with the molecule. And inspired by XP-PCM, we came up with so-called GOSTSHYP method. And GOSTSHYP stands for Gaussians on surface tesserae simulated hydrostatic pressure. And we, that is Maximilian Scheurer, he was a PhD student in Andreas Dreuw's group in Heidelberg. And actually yesterday, Max defended his PhD thesis. So congrats to that. And everything started back in Berkeley when I was working with Martin Head-Gordon, and Evgeny from Q-Chem was also a tremendous help on this project. So thanks to everyone for making this project, for making this work. And in XP-PCM, in GOSTSHYP, what we're doing is on each surface tessera, we're putting a Gaussian potential. And these Gaussians have the regular form that you would expect. You have this, you have an amplitude factor. Usually when you think of Gaussian functions, this is a normalization. But here we call it an amplitude. And I'm going to tell you why in a second. And then in the exponential part, we have our regular expression here, and we have a width parameter, Wj. Yeah, I'm not going to go into much detail how we are calculating those two parameters. But first of all, the basic idea is the following. If the pressure is low, then our Gaussian potentials are weak. So we have a weak interaction between our Gaussians and the electron density. And if the pressure is high, then we have strong Gaussians that interact very much with the electron density of the solute. And yeah, the workflow is the following. We can calculate the energy contribution by GOSTSHYP by summing up over all our tesserae, or all of our Gaussian potentials. And each Gaussian potential contributes the following term to the energy. It's just the Gaussian itself multiplied by the electron density. And if you just write this down rigorously, you find three center overlap integrals contracted with the density matrix. And yeah, the first step is what we need to do is we need to determine the parameters of Gj. Those are the amplitude and the width parameters. And on the next slide, I'm going to give you like 1 or 2 hints how we're doing that. Then we're calculating all the 3 center overlap integrals. And then we're adding this energy contribution to the energy in the SCF. So we get a physically sound energy of our Gaussian potentials, of our pressure contribution. Of course, there are also Fock builder contributions. We are adding them, so we're doing a proper SCF under pressure. Yeah, we're also calculating the gradients because you want to do geometry optimizations or ab initio molecular dynamic simulations. So we also need the gradients, and we're adding those to the nuclear gradient in geometry optimizations or ab initio MD runs. Now, just a word on how we pick the width parameter. We would like to ensure a very smooth field of Gaussians. So if you have two neighboring Gaussians, in the middle point between those two, we want to have the one Gaussian have half of its maximum value, so that neighboring Gaussians overlap in a constructive way, and we get kind of a smooth field of these Gaussians. And that's just a simple equation how to do that. You can look that up in the main paper, and this is done by the program for you. And now for the PJ, these are the amplitudes, and this is really the core work in GOSTSHYP, how to adjust the amplitudes in such a way that the externally applied pressure that the user inputs, that's actually applied to the molecule. The key again is this basic equation of pressure, and you're doing a couple of derivatives to get the forces here, and you do quite a lot of algebra, and in the end you end up with a expression for your PJ amplitudes for each Gaussian. Now enough of this theory, let us look at how GOSTSHYP performs with respect to energies. And we see here the blue curve is GOSTSHYP, and it seems to be in kind of a very good agreement with our reference. There are more than 30 years lying between those two theories, and the theories are completely different, but qualitatively they give almost identical results basically. I wouldn't want to hazard a guess which method is more reliable, but in any case we're getting much closer to our reference values than with HCFF, with X-HCFF. We tried a couple of different things, but you can also do with GOSTSHYP, for example, dipole moments. Dipole moment of water has been looked at theoretically by a couple of people. For example, in this paper here, I'm unfortunately not allowed to show you the picture I would like to show, but what GOSTSHYP gives is if you increase the pressure, even in the terapascal regime, that's only a theoretical regime for at least us on Earth, you first get an increase in the dipole moment of water, and then you get a decrease again. And without showing you the main plot, you can look this up yourself. This is qualitatively the same behavior that they found in the previous paper. You get an almost 20% increase in the dipole moment of water. And X-HCFF gives a completely different result. And the reason again is quite clear, because dipole moments are very tightly linked to electron distributions, and you don't get the correct electron distribution in X-HCFF under pressure. So GOSTSHYP performs much better. We looked at a chemical reaction. In this case, we skipped the CO2 dimer, and we instead looked at a Diels-Alder reaction, because a Diels-Alder reaction is something that was really, that has been really popular for many years and many decades, experimentally and theoretically, to do that under pressure. That's a classical example. And what we get here is, if you measure the distance between the diene and the dienophile, you get a decrease in this distance with increasing pressure, and suddenly you get a steep drop at 40 gigapascal. So in our calculation, at 40 gigapascal, you get the product of the Diels-Alder reaction here. So chemical reactions are also not a problem. Unsurprisingly, the user input almost looks exactly the same as previously. The only difference is you put in GOSTSHYP here as the model name. You can even do this with Born-Oppenheimer MD simulations, or more generally with ab initio molecular dynamic simulations. That's also implemented in Q-Chem, and this is the same reaction, the Diels-Alder reaction of cyclopentadiene and ethylene. Here we immediately apply a pressure of 40 gigapascal just as a proof of principle, and we ran 10 trajectories. And we showed, we basically saw that you get these oscillations here of the van der Waals complex, and then depending on the statistics on the initial velocities that you choose randomly, sooner or later you will end up in the product of the Diels-Alder reaction. And we can have a look at this. We can have a look at this. I don't know if I can do that like this. Yeah, we can have a look at this dynamically. Yeah, you kind of quickly you get the Diels-Alder reaction, and now it just oscillates around with some kind of a damped oscillation here. I'm just going to run through this again. You have tiny little motions of the van der Waals complex, and then quite quickly in this particular trajectory, you get the formation of the product of your Diels-Alder reaction. Here it looks a tiny little bit differently how you input how you do the input, but the main differences are just in the $rem section. Here you need to specify drop type AIMD, and I'm not going to iterate or reiterate how this is done. You can look at this in the manual. There's like a very nice section on all the parameters that you can or need to specify in BOMD runs. What's important is you also need to specify to store to true. And now you put in GOSTSHYP, or in fact this works with HCFF and X-HCFF, whatever you want to take there. Just one more point. In this case, we've taken scaling 1.8. That's a technical intricacy, because what you want to do is, if you go back for 2 slides, what you need to do if you model a chemical reaction in GOSTSHYP, it's very important that you house this whole complex into one. You basically put this into one cavity. If your scaling factor is too small, then ethylene has its own cavity, and cyclopentadiene has its own cavity, and they don't get pushed together. So you need to increase the scaling factor so that everything is just one cavity. But in GOSTSHYP, we showed that the result, just energies, geometries, as long as you don't look at chemical reactions, those results are quite unsensitive to the choice of the scaling factor. So we're kind of safe actually. Now let me summarize the pressure part of this talk. In GOSTSHYP, or we're just adding GOSTSHYP here. We now see that the electron density is compressed in a physically meaningful way. We still get sensible geometries, chemical reactions. We could model them statically and dynamically. We can still specify the pressure a priori. And now I've put a question mark next to steep scaling. We need to realize that GOSTSHYP basically scales as n basis functions squared times the number of Gaussians. The number of Gaussians increases rather quickly. Even for medium-sized molecules, you can have more than 1,000 or a couple of thousand tesserae, which then lead to a couple of thousand Gaussians. And yeah, that's a little bit of a scaling problem. For example, just on these computers in my group, we could calculate smaller fullerene-like structures like C20, C24, C40 was okay, but we could not calculate C60 just because of memory issues and then also time issues. That wasn't just practical. But Felix Zeller in my group is taking some very interesting and very helpful steps in the direction of reducing the scaling. And our ultimate goal is to make GOSTSHYP as expensive or as cheap as a regular, say, DFT calculation during a geometry optimization. That's our goal. All right, I'm not finished yet. I'm going to transition to the final part of the talk, where we're not compressing molecules, but we're applying forces to stretch molecules apart, just doing the opposite motion. And this falls within the range of, or this is basically the field of mechanochemistry, or in our case, quantum mechanochemistry. You can read up on this here, and this is yeah, there are a couple of experimental techniques for those people who do not have the dexterity to take single molecules in their hands and stretch them apart. And let me first give you the user input actually, just to show you that. Still, your $rem section is the same. You're doing a geometry optimization. You still need to include distort true. And now in the $distort section, you're specifying model EFEI. So EFEI is a very nice method. In 2009, there were a couple of related papers on how to do mechanochemistry quantum chemically, and the EFEI method was introduced in this paper here. And what you're doing is you specify a pair of atoms. And this pair of atoms, you calculate the vector between them and calculate the vector pointing outwards. And then you're just adding a constant to the nuclear gradient of these atoms during a geometry optimization. And the forces basically are driving those atoms apart. You can also apply compressing forces, but just between the two pairs, it's all possible. And in Q-Chem, what you're doing is you have this line force, and then you have atom 1, atom 2. Those are just the indices of the atom pair that you want to drive apart. And force 1 here is the force in nanonewton. Typically, your forces are in the range of a couple of nanonewtons, sometimes only piconewton, that you need to rupture bonds. You can do that for other pairs of atoms as well, but usually we only take one of these lines here. Let me give you an example what we can do with that. Here we actually did BOMD simulations, and we couple this with a force analysis. This is why this coloring scheme, where this comes from. Here we have the molecule completely relaxed, and this force analysis allows us to track the strain in this molecule. There has been quite a debate for the last decade or so if you can rupture these triazoles mechanically. This was kind of a fierce debate actually, and we looked at this quantum chemically in this paper. And let us have a quick look at how this is done, or what happens if you apply stretching forces to the chain ends. You see that the strain kind of propagates from the end to the middle. Get a buildup of strain here in the triazole region, then the strain oscillates back and forth a little bit. Yeah, at this point it's still in the middle. It oscillates one last time, and let us see what happens now. Yeah, what happens now is the strain was too high, and you get a rupture of this triazole moiety. The whole story is quite more complicated. So if you're interested in that, please check out the paper. I'm not going to say that this is what happens all the time in the experiments. Rather, the opposite is true, but this was one of the trajectories and one of the configurations where you actually get the cyclo reversion. And now, finally, I would like to point you to a very recent application that we did with Surab Kumar and Felix Zeller. Both of them are working in my group. We looked at spiroporane. Spiroporane is a classical mechanophore, and a mechanophore is a molecule that, if you apply forces to a mechanophore, then you have structural rearrangements of bond rupture. And in this case, you can rupture this carbon-oxygen bond here, and you get merocyanin. Maybe some of you know this as a photochemical reaction. This is discussed as a classical photoswitch as well, but it has been known for like 10, 15 years that you can induce this rupture mechanically. And there have been, I'm sure there have been hundreds of papers and many reviews on how to do that experimentally. This is being used as an optical force sensor actually, because you get a color change. You go from spiroporane to merocyanin. It's quite an interesting topic, but quite a lot of work has been devoted to that already. What has been significantly less well looked at is that you can induce the back reaction by applying pressure. And we realized that this can be done because merocyanin has a larger volume than spiroporane. So according to Le Chatelier's principle, you would basically bias the back reaction by applying pressure. And we showed that this is possible. We applied stretching forces to spiroporane, and we applied compression, in our case with X-HCFF, and we got spiroporane. And we also showed you can do this in a cyclic way. So our paper is called baromechanical cycle. And the application of this idea, they might actually be quite interesting, because usually these materials that incorporate these mechanophores, you can use them once, then the mechanophore is activated. And there are only a couple of approaches how you can reverse this. And now we're basically suggesting of establishing pressure to revert this process. We did some BOMD simulations. First of all, we're starting with myrocyanin here at 0 time. And in this gray shaded area, we are increasing the pressure. Now, if the pressure is large enough, typically in the region of like 1 or 2 gigapascal, we get a sharp decrease in this distance between C and O. And here, spiroporane is formed. Now, in this white area, we are slowly increasing the stretching forces. And if the stretching force is enough, that's typically in the region of a couple of nanonewton, you get an increase in this distance, and this means myrocyanin is formed. Again, we switch to pressure, and now spiroporane is formed again. You can basically do this back and forth over and over again. And quite beneficially, the UV-vis absorption spectrum changes quite tremendously during these back and forth isomerizations. You're starting back here with the myrocyanin spectrum. It's kind of broad, has a lot of peaks. And we calculated the spectrum just in every point of the BOMD trajectory. And if you move in time, at some point you can clearly see the formation of spiroporane. It's much smaller or more narrow. Then again, you generate, by stretching force, you generate myrocyanin, you get this broad spectrum here. You switch again to spiroporane. And yeah, we suggest that if you do that experimentally, if you find a way to couple stretching forces and compressing forces, you would then also get a color change. You could track that in real time by the naked eye. All right. Yeah, I think I basically leave you with this final summary of what you can do in Q-Chem now with applying pressure and applying forces. This was generated, this nice picture was generated by Surab, and it gives you a good opportunity, a good overview of what can be done with this dollar distort section in Q-Chem. I thank you very much for your attention, and I'm happy to answer your questions.
Thank you, team, for this informative and interesting talk. We have a couple questions there. So the first one, for the extended HCFF, can you comment on getting the correct chemical reactivity with not so physical electron density?
The correct reactivity with a with basically an incorrect electron density. Yeah, the question is a little bit what do you mean with reactivity? Yeah, you can basically wonder, why do we get chemical reactions at all if the electrons are not compressed as much? That's really a very good question. What you would probably need to calculate would be reaction barriers, right? This would give you, I think, a very good hint about energetics, also about where is the transition state. And yeah, I think that's something that we should definitely try out in the future, and maybe compare X-HCFF with GOSTSHYP. Yeah, thanks a lot for this question. I actually take that as a useful suggestion for future research. Yeah.
Thank you. So a second question for the GOSTSHYP, can you comment on the computational cost? And I think you already mentioned that in the talk. It's n base squared times number of Gaussians, right? Mm-hmm. So right. The attendee has issue with the convergence using this method, he has around 40 atoms in the system. Is it because that kind of reached the limit for this method?
Yeah, interesting question. So 40 atoms was for us the limit that we could run on our workstations. Those are, medium, I would say, medium powerful workstations. And yeah, we had some issues with memory and with runtime, but I think this should not matter concerning the convergence. Probably the attendee means SCF convergence. And if this is the case, I think this should not be influenced by the size of the system. I would be very curious in seeing the molecule, because in most cases, or in almost all cases, we did not have any tremendous problems with SCF convergence. Sometimes we encountered those, but this was in general not a problem. So we would be very, very interested in that. And yeah, so if the attendee wants to give us a hint about this, I'm very happy to look at the molecule, and maybe we find out why we get problems with the convergence.
Thank you. I guess myself a follow-up question. So for the scaling, is it any plan to reduce the scaling? So right now is is the number of Gaussians proportional to the number of Tesla point?
Yeah.
Or its number of Gaussians just the number of Tesla point?
What we're doing is just if you generate this grid, each tessera has one Gaussian. There's a one-to-one mapping, and we can specify this by this endpoints. And we saw that in many cases 110 gives you kind of a good compromise between a smooth field of Gaussians and yeah, basically the good accuracy, good convergence, and these kinds of things. And now we can, well, a very rough estimate would be if you have like 10 atoms, then the number of tesserae would be 110 times 10. But it's not as simple, because what the algorithm does is you have overlapping regions between these van der Waals spheres, and those are cut away. It depends very much on the molecular shape, how many of those you cut away. But yeah, I would say that with 10 atoms, you probably have like, I don't know, 700 Gaussians, something like that. But this can grow rather quickly. And yeah, like I said, it's the scaling is n basis functions squared times the number of Gaussians that remain in your system.
Okay, thank you. And then we have two more questions. The first one, is it possible to predict phase transition via pressure with your method?
Oh, yeah, that's also very interesting. Phase transitions are something that's, if you look at experimental high pressure chemistry, that's like the forefront of what they want to look at. Also in periodic codes, that's something that people have modeled. We have not done that yet because we have not really delved deep into periodic calculations. In the future, we want to do that, and actually we started that with comparing different computer codes. But right now we did not do that in Q-Chem. However, there's basically no theoretical limit. If you have periodic boundary conditions and you have a crystal and you would use GOSTSHYP, then I cannot think of a reason why you should not be able to model phase transitions in general.
Thank you. So next question also about the computational cost. Can you comment, is it the cost for the mechanochemistry application also scale with the n base square times the number of the Gaussians?
This is the mechanochemical models, HCFF and X-HCFF. They are basically exactly as costly as a regular geometry optimization, taking the level of theory that you want. There's no additional computational overhead. Sometimes it takes like 1 or 2 geometry optimizations longer, but each geometry optimization cycle or each SCF, each gradient calculation is like almost 100% the same as a regular pressure-free step. And because what you're only doing is, say we have X-HCFF. Where do we have that? Here, you're just calculating these vectors and you're just adding a bunch of vectors. It's a couple of hundred or a couple of thousand, but yeah, it's just very, very quick.
Mm-hmm. Thank you. We don't have more questions. Okay, I'm gonna move to close this webinar, and if you have more questions later, feel free to email me or post a question in our talk forum. And I would like to thank team again for this wonderful talk, and it's a really nice and interesting talk. And I also want to thank our attendees for listening.
Thank you.
Thank you.
This concludes our webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.